These young men are engineers engaged in the development of an engine management system for a new gas turbine. Theirs is a meticulous and seemingly unglamorous world. The results, however, can be dramatic. 25 years ago, Lucas were creating the engine management system for this aircraft. Today, as Lucas engineers develop the new designs and engine systems for the 21st century, they're continuing a pioneering tradition that stretches back 50 years. 50 years at the forefront of gas turbine technology. 50 years at the leading edge. (1940). Then, the all-metal monoplane represented the latest in technology, and the piston engine had still to reach its full potential. And yet, there were those whose vision and dedication were to revolutionize air transport. They were developing Britain's first jet aircraft, the Gloucester Whittle. Its revolutionary propellerless engine was the brainchild of a serving RAF officer, Frank Whittle. Also included in the project was a company then better known in the car industry, Joseph Lucas. Lucas Gas Turbine Equipment, as it was called, forerunner of today's Lucas engine systems, was engaged on the design and manufacture of the fuel and combustion system. The whole project was, of course, top secret, although later the public were given a layman's guide to the jet engine.
The turbine, which can be seen revolving, drives the centrifugal compressor, which compresses the air taken in through the nose of the aircraft. This air, under pressure, is passed through the combustion chambers where the temperature is raised by burning fuel with it. The hot gases are then expanded through the turbine and finally ejected at high velocity through the tail jet pipe.
All very simple in theory. In practice, it was pioneering in its truest sense, often by trial and error. On the 14th of May, 1941, Britain's first jet aircraft was ready to take to the air. Central to the success of the fuel system was the development of the Lucas variable displacement piston pump, able to respond to specific demands made upon it. In short, a smart pump. The Whittle jet was, however, purely an experimental aircraft. What the country needed was a jet fighter.
These are the first pictures to be released of the Gloucester Meteors, Britain's jet-propelled fighters, which did such great work.
In July 1944, the RAF took delivery of the first squadron of operational jet fighters. They were twin-engined, powered by the Rolls-Royce Welland.
Compressed, heated, and then ejected through the turbines and nozzles.
By this time, Lucas had incorporated a barometric pressure control, which gave pilots more consistent engine controls at altitude. By the end of the 1940s, Lucas were producing a series of pumps and engine controls that had become generic equipment for Britain's frontline jet aircraft. The post-war years also saw a great upsurge in the demand for civil aircraft. People wanted to travel. The gas turbine, with its smooth power, was an obvious choice for this new generation of aircraft. The de Havilland Comet, the world's first jet airliner. It was powered by Rolls-Royce Ghost engines, using Lucas engine control equipment. Rolls-Royce were also using Lucas equipment for its new Dart engines. These powered the Vickers Viscount, the world's first turboprop airliner. The 50s saw many new types of aircraft using Lucas equipment, both civil and military. Aircraft such as the Gloucester Javelin, the world's first twin-engine delta-winged fighter. And Lucas entered the supersonic age with the English Electric Lightning, Britain's first truly supersonic fighter. Over the years, as speeds increased, so had the need for more sophisticated engine controls. Controls which would increase the element of self-regulation and so reduce the workload on pilots. On the earliest jet aircraft, engines like the Whittle made use of simple pressure controls to regulate the power. Pilots had to guard against engine stall and the flame-out. On the early Meteors, powered by the Welland engine, the barometric pressure control was just the first of the many developments Lucas were to introduce over the next 20 years, making engine controls more user-friendly. However, in the early 1960s, this combined acceleration and scheduling control fitted to the Rolls-Royce Spey engine represented a real breakthrough. Here, as the pilot opens the throttle to increase power, the system limits overfueling, preventing surge, but still allowing the engine to accelerate to the selected speed. Conversely, when decelerating, the engine is protected against underfueling. The result is a lessening of the workload on the flight crew and greater engine efficiency. In 1964, the Hawker Siddeley Trident was the first civil aircraft equipped with this generic non-dimensional engine control. Before long, the Spey engine with this unique closed-loop speed control was being specified for many aircraft. Many of the principles of this system were to be embodied in Lucas's next generation of engine management systems. By the end of the decade, these full-authority fuel flow regulators were being fitted to the Rolls-Royce RB211 engine. Engines that were to power the new wide-bodied jets then coming into service, the Lockheed TriStar and the Boeing 747, and provide greater control and greater efficiency. This aircraft captured the world's imagination and brought the promise of supersonic flight to the paying public. The Anglo-French Concorde gave new meaning to the Entente Cordiale, and its powerful Olympus engines were unique in having a Lucas all-centrifugal fuel pumping system. As the new shape took to the skies, another revolution was making itself felt on the ground. The age of the computer was with us. As long ago as 1948, Lucas had flight-tested simple electronic controls, and development continued in the 50s and 60s. However, the advent of compact, reliable computers opened new possibilities. Engine control could now become engine management. Computers have the ability to monitor large amounts of incoming data and to respond instantaneously. Computers, however, can't operate aircraft engines on their own. To complement their computers, Lucas also designed interfaces that would translate each of the computer's commands into a physical response, creating a full-authority digital electronic control, or FADEC. In 1976, installed in Concorde, the system successfully completed its proving flight trials, a world first for Lucas. Panavia Tornado, backbone of the RAF's contribution to NATO. Its full-authority electronic engine control was a practical result of Lucas's early development work and one of the first in service in the world. By the late 1980s, Tornadoes would be flying with fully integrated digital main engine and afterburner controls. A far cry from those simple fuel pumps of 50 years ago. Those same 50 years have also seen great changes in the design and production facilities at Lucas. Sites at Birmingham and Liverpool producing the precision components and systems are equipped to meet the needs of this high-technology industry. The same original approach that marks Lucas's engineering is also evident on the factory floor. Here the workplace is cellular, organized into small units, each operating as a close-knit team, It's a move which has seen quality increase significantly, with a corresponding reduction in costs and a dramatic reduction in lead times. Engineering is organized on a project basis, each with its own program manager.
40 engine sets, which is really a major order. Of course,
the customer benefits by having a single point of contact for all aspects of the program. And looking after the customer's needs extends far beyond the factory gates. Conveniently placed near Birmingham Airport is the engine system's repair and overhaul base, which services all types of fuel pumps and systems. In turn, it's backed by a worldwide network of spares and facilities. Over the past 50 years, Lucas Engine Systems has produced over 60,000 fuel pumps and control systems for more than 100 types of aircraft and is now the major supplier in Europe. It's reached that position by investing in research, future developments that are often many years ahead of their time. For these engineers and scientists, it may be many years before the results of their efforts take to the skies. And in this particular case, the sky's not the limit. This is a cryogenic cooler designed for use in deep space. It produces very low temperatures vital for certain instruments. It dispenses with the need for the spacecraft to carry large volumes of heavy cooling materials. Under development for the US space program, it's a world leader. Whether in deep space or closer to home, Lucas has a commitment to developing new technology. Lucas equipment for electronic controls was the first to be certified in America by the FAA for use on helicopter engines. The Osprey, Bell Boeing's revolutionary tilt-rotor aircraft, uses Lucas controls for its Allison engines. And in this age of European cooperation, Lucas is providing all power plant fuel pumps and metering units for the four-nation European fighter project. Indeed, the next decade will see proven Lucas systems taking to the air in a whole range of new aircraft. The past 50 years have been a period of quite remarkable development in aircraft technology. The next 50 years promise to be no less challenging. But whatever the 21st century may bring, Lucas will continue its pioneering development, ensuring that it remains at the forefront of aerospace technology, at the leading edge.